Hello everyone, Robert here. I'm going to make a video for my student Michael out in Colombia, and this video is on differentials and linearization. Okay, so what the fuck is linearization? If you have a graph and you have some interesting function that you want to, here's f of x, and this function you want to evaluate at this value a. What you can do is, instead of actually evaluating this function, and it could be something really complex, and also the value of a could be complex, what we could do is we could build the slope or the equation of a tangent line at or near that point. And if you were to zoom in, and let's go ahead and draw that tangent line. If the tangent line is centered at this value of a, and if we were to deviate from that value by some small change in delta x, either we go to a value of a minus delta x or over to here to a plus delta x. If we were to plug in a plus delta x into the actual function, where this is the function here and then this is the equation of the line, you can see that both values are not too far off. The values centered at a, this is when they're equal, when the function itself and the linearization function are equivalent. But we're not interested in doing it just at that center point. We're interested in seeing what values can we extract from an easy equation of a line if we were to move a little bit away from that value of a. And so this is what kind of gets into. So function square root of x, something pretty easy. If we were to take the root of 4, oh cool, we get a 2. But what if I wanted to take the root of 4.01? And, yeah, it's kind of ridiculous. Like, you guys would say, who the fuck wants to do that? Let's just bust out a calculator, figure out what the fuck it is, and be done with it. Well, that's the thing. What if we were to, I don't know, what if some sort of weird nanotechnology came out and wiped out all the technology everywhere? Well, then you couldn't even actually see this video, so fuck. But this is what it's getting at. Here's a square root function, and when you plug in 4, you should come into a value of 2. And I'm going to exaggerate this. If you plug in 4.01, you're going to get a value that's not exactly equal to 2. And instead of actually plugging this into your calculator, the root of 4.01 is going to be equal to some decimal value. There's a dot. What I want to do is I want to see if we could use some sort of what's it called, a shortcut or a way to approximate this guy. And so at 4, what we could do is we could build the equation of a tangent line, and then we could use that equation of a tangent line to go on over 1/100th of a point and see what this guy's y value is compared to the functions. And they're actually really good approximations of each other. Okay. So really quick, when you want to find some y value, you're going to evaluate some function f of x. And the x value is usually going to be something nice. But what if we were to, instead of using x value of really nice, that's like the root of 4, our x value would be 4. What if we were to say, let's go on over a smidge, and this is like saying taking the root of 4.01. How would we evaluate the function at x plus delta x? I mean, we could just, again, use a regular function, plug in the root of 4.01, and then bam. But that's besides the point. We're not trying to do the exact method. We're trying to use something called a differential. Now, when we undergo some small change in x, so here's that square root function. Here's a value of 4 that maps out to a value of 2. When we plug in 4.01, we get a little higher value. And this is a really shitty drawing, but this small difference between the two y coordinates is known as a delta y, just a change in the function's y value. So what I could say is, if I'm going to change the function's x value that I'm going to evaluate at, I could take my original function and add some small change in y, okay? And here on the right side, this is my traditional expression. Like, I want to evaluate the 4.01 square root. I want to see what it is. On the left side, this is what you're going to be doing. Your y is just your expression, the function at 4. This would just be the square root of 4, and you know that to be 2. this delta y is what we're interested in. We're interested in finding out the small change in y. And what we want to do is we don't want to use a traditional way of finding that. We don't want to say, hey, it's my function at x plus delta x, that's the new y coordinate, and then minus the original function f of x. That would just suck. What I do want to do is I want to say that this can be approximated by a differential dy. And if y were f of x, then a differential dy is just the derivative of that function times the differential dx. And in this problem, when we're taking a look at the square root of 4.01, what we want to do is we want to write it as something really nice and easy, and then plus this small little change. This is our original x value, and this is our delta x, or this is also our dx value, okay? So if I wanted to approximate the root of 4.01, what I could do is I could just say that it's the original function at 4, just the root of 4, and then plus some small differential change in y. I don't want to use a delta. We're using calculus. We're going to approximate this using a differential. So here's the root of 4, and then I want to add a small little change dy. Now my original function is the square root of x. If I were to find the differential, so if my y was f of x, which is the root, my dy is the derivative times a differential. And if I took the derivative of the root of x, use the power rule, you get this 1 over 2 root x business, and then you have a dx. So when I approximate the root of 4.01, again, I could use the original function at 4, which is just the root of 4, which gives me a 2. And then what I'm going to do is I'm going to use this differential expression, and I'm going to evaluate it. My x value, my really nice value that I centered at, is still 4. So I'll have this 1 over 2 root 4. And then I multiply by the differential change, dx, and it's a value of 0.01. That's that small change in x. Okay? And if I work this out, the root of 4 is a 2. I have a 1/4 here, and I'm multiplying it by 0.01. So this is going to be 2 plus like a 0.25 multiplied by 0.01. And what that does is it moves the decimal point over 2 times. So this is 2 plus 0.0025. And what we could do is we can approximate the root of 4.01, my bad, and say that that's 2.0025. Now, let's see what the square root of 4.01 is on a calculator. So I'm going to go ahead and open up my cell phone's calculator. I'm going to type in 4.01 square root, and it actually gives me 2.002498439. What if we, so here's the tens, hundreds, thousands, 10,000s, 100,000s, millions. If we even rounded to the millions place, that would cascade, the 8 would go up, the 9 would go up. This would be 2.00250. And look at that. I mean, that's a pretty damn good approximation. Actually, it's just about exact. We don't want to use exact. We don't want to say exact because there's no such thing. But this is how you use differentials. So whenever you want to evaluate some function at a really nice value, but then we deviate from that value, we want to use the function y, which is just the original f of x, and then add a small change in delta y, or we can regard this as a dy. And then by definition, we are regarding this as dy as an f prime of x dx. That's our small little change. So just for another example, what if we were to be taking the, let's just say that we're going to take the 3.05 and we're going to cube it. So this is what I'm going to do. I'm going to take 3.05 and cube it, and I want to see what the value is. Now, what would be nice is if this was just plain ass 3 cubed. I don't want to say f of x really right now. If this was 3 cubed, it would be something easy. It's 27. But what this is 3 plus a very small change in x getting cubed. And yes, we can work this on our calculator. If I take 3.05 and I cube it on my calculator, I get a value of 28.372625. That's the exact value if I were to work it on out. Now, how would I use differentials? I'm cubing something, so my original function is the cube of x. My x value that I'm interested in is cubing 3. It's what makes life easy. And this small change, this differential dx, is that 0.05. It's that small little value that I added to x. Now keep in mind I could have done 2.95 and my dx value would have been negative, but I'm just using positives in this case. So if I want to evaluate my function at this x plus dx, or delta x, what I could do is I could say that this is my y plus my differential change dy. My y is my function at the original value of 3. My dy is the derivative at 3 times my differential change. So right here, my function at 3, it's 3 cubed, we have a 27. My derivative at 3, the derivative is a 3x squared. So really quick, if I wrote up here, my f prime of x would have been 3x squared. So if I were to take 3x squared and then multiply by that small differential change of 0.05, what I would have is I'd have a 27 times 0.05. And let's just see what that comes out to be. So if I take 27 times 0.05 on my calculator, I get a 1.35. So this guy fully comes out to 28.35. That's the differential approximation. Look at that, 28.35, which is the approximation, versus the actual value, 28.37. It's off by 2/100ths. Not that big of a fucking deal, all right? This only really works, the differential, these small approximations work if that, this change dx is pretty small compared to the number. So I'll give you an example, like if you were to be taking the square root of 8 and then saying, oh, well, that's the root of 4 plus 4. Well, that's way off. I mean, this is not really a small change compared to the x value. But you could also write the root of 8 as 9 minus 1. So your differential change of minus 1 compared to 9, that's not that bad. But we really want to look at even smaller changes. So if we were to take the root of like 9.5, that's 9 plus 0.5. That's a decently small change, okay? There's not really a rule. Usually when you encounter these problems, they kind of set them up for you. They say, like, hey, what's the cube root of 63? Well, that's the cube root of 64 minus 1. So there's your central value of 64, and a cube root of 64 is really easy. It's 4. And then your change is a very small value. Dx is -1, and when you compare -1 to 64, again, like you're in the ballpark of saying, okay, that could be a decent change. Okay, so I hope you can appreciate this tool. It makes life easy when you don't have a calculator and you can do some basic operations and work around evaluating functions at really nice numbers, such as the root of 4 versus the root of 4.5, or the root of 9 versus like the root of like 9.5, and so on and so forth. Okay, hope you enjoy that, and take care.